Greetings everyone, I'm Shashwat Mishra and today I'll be presenting my project that is statically tuned room temperature phosphorescence in N-substituted phobromethalamides, which is a minimalistic organic scaffold for metaphyllominophores. To break down this topic, I want to talk about the phosphorescence behavior, that is a special kind of a special kind of photoluminescence phenomena, where when the electron is excited from the ground state to the singlet state, instead of directly returning from that singlet state to the ground state, the electron takes a second pathway where it transitions to an excited state called as triplet state, which involves the flipping of the spin of the electron, and thus this particular process is also called as intersystem crossing. Because this particular pathway now becomes spin forbidden, the emission is very slow and it is actually delayed. So thus the phosphorescence is actually delayed in nature and it takes microseconds to seconds as compared to fluorescence, which is very prompt and fast and happens in nanoseconds. Also, why does phosphorescence and how does phosphorescence relate? We all have seen those glow in the dark toys or glow in the dark safety signs in our daily life. They even glow when the light source is turned off. That is because of the fact that the phosphorescence takes from microseconds to seconds to minutes, depending on the compound and the nature of the material involved there. Phosphorescent materials have much more broader use case in their everyday life and in the scientific community. They're used in the organic LEDs, optical storage devices, also in the anti-counterfeiting inks. They've been increasingly used in the bioimaging, where they have been used to study cells and the different kinds of biomechanical and the biochemical processes involved. They're also used in the time-resolved imaging of the different kinds of materials. They also help us in a very wide case scenario use case, that is a glow-in-the-dark safety science. Pertaining to this widespread use case of the phosphorescent compounds, the conventional RTP systems are solving this issue, but they have certain limitations in them. They are very big and complex, and because of their big and complex structure, they require a multi-step and a tedious synthetic routes that is not at all economical and is expensive and hard to make. And also, the synthesis of these compounds is not eco-friendly because they involve the use case of iridium, ruthenium, and platinum, which are all heavy metals, and they lead to heavy metal pollution. To answer this limitation, we tried to suggest this particular simple compound called as 4-bromothalamide, which we hypothesize will have a good phosphorescent behavior and has a promising characteristic for the photoluminescence study. We are suggesting this because this particular compound is rigid and planar and it's very similar and thus requires a very minimalistic synthesis pathway. Also, we have modification areas on the end substitution by which we can tweak and fine tune the emissions that are involved in the photoluminescence. Especially as we have all talked about that this indirect pathway through the triplet state should be very much stabilized. So the bromine and the carbonyl group help us stabilize the triplet state and help us promote the intersystem crossing, and the phosphorescence pathway is much more favored for this compound, is hypothesized to be much more favored as compared to the fluorescence pathway. So the aim of our study is to balance between this ease of synthesis and also the optical performance of a compound, and we would also like to study the substituents with the free and the substituted side groups and their effect on the core and the phosphorescent behavior. The compound was synthesized using a systematic scheme for synthesis of 4-bromo-N-aryl or alkyl phthalimide. We employed 4-bromophthalic anhydride with some primary amine. Under the toluene solution at 110 degrees Celsius, we obtained a scaffold of 4-bromo N-substituted phthalic anhydride. Phthalimide. We got 4-bromo phthalimide, where we can also modify the N substitutions on our end. Pertaining to this, we tested 3 different N substitutions. One was N-butyl, which is actually a free alkyl chain. Then we had a N-isopropyl group that is much more branched and is thus much more crowded as compared to N-butyl chain. Then we also implied alpha-methyl benzyl group, which is much more crowded and sterically hindered as compared to isopropyl, and even more crowded as compared to N-butyl. An important idea to discern here is that if you see from the left to right, as the compounds are increasing, as the compounds are shown, the bulkiness of the N substitution increases, and thus the substitution is much more sterically hindered. We employed the standard lab techniques to synthesize our process. A one-step imitation actually produced our minimalistic target molecule. After isolating the organic layer from the reflux setup, we purified the compound using column chromatography, and the crystallized product obtained after purification was first characterized under the standard lab protocols of NMR and HRMS, where we tested the proton NMR and the 13C NMR to validate the structure of our compound. Moving on, we tried to analyze the photoluminescence behavior of the compounds. For this, we did the analysis in the solution state and the solid state. Coming up to the solution state, we observed that we first want to note what is the excitation wavelength of the compound. We found that by running a UV visible absorption spectra in the dichloromethane solution, we observed that for all the three different substitutions that we did, the maximum absorption was happening at 300 nanometer, which is pertaining to the N to pi star transitions in the three different compounds. The similar wavelength suggests here that the core involved here is 4-bromothalamide. Then we ran the fluorescence or the prompt emission analysis of our samples in the dichloromethane using the solid state photoluminescence spectrometer, where we found that both N-butyl and the isopropyl substitution have the maximum fluorescence peak at 390 nanometer, but we see a slight blue shift in the alpha-methyl benzyl substitution, which shows its maximum intensity peak at 360 nanometers. We tried to study the phosphorescence behavior in the solution state too, and we found that, as it is shown in our diagrams too, for the three different substitutions, almost no phosphorescence was observed in the three different in the solution state. We only found weak fluorescence, which happened at 390 nanometers for the N-butyl and the isopropyl, and 360 nanometers for the alpha-methyl benzyl group. This particular blue shift in the compound can be attributed to the fact that alpha-methyl benzyl group has a complex energetics involved, especially because there is an aromatic ring involved in it, and also because this particular compound is much more rigid and compact as compared to the N-butyl and the isopropyl substitution. Thus, it better favors more organic phosphors to excite to the higher energy state, and thus the emission intensity is changed. Now we tried to study the compounds in the solid state. To study this compound, we ran the excitation scan of the three wavelength, and we found that all the three different compounds had a consistent excitation wavelength of 340 nanometers. Then at this particular 340 nanometer, we ran the photoluminescence analysis in both the fluorescence and the phosphorescence analysis in the solid state, and we found that both the fluorescence and the phosphorescence happens at the maximum peak of 460 nanometer for all the three different compounds. This is actually a peculiar character here, because usually the triplet state or the ground energy state band gap is much more different as compared to singlet state band gap. But this shows that the energy gap between the triplet state and the ground state and the singlet state and the ground state is actually similar. This can be actually discerned by the fact that some of the usual organic phosphors in the solid state, especially because of complex association and a compact structure and the solid state electronics involved, they have a much more synergy and a much more degenerate triplet state and the singlet state, and thus why we observe a similar band gap on each of them. We tried to study the intensity of phosphorescence emissions in the three different substitutions, and we found that as the bulkiness of the N substitution got increased from N-butyl to isopropyl to alpha-methyl benzyl group, the intensity of the phosphorescence emission was increased too. Especially a high jump was observed in the alpha-methyl benzyl group from the isopropyl group. This can be again attributed to the fact that alpha-methyl benzyl group is a much more rigid substitution, and it helps pack the molecular structure much more in the solid state, and thus more of the compounds and more of the organic phosphors are excited to the higher energy state and are favored into the phosphorescence pathway, and thus we observe an increasing phosphorescence intensity in the alpha-methyl benzyl substitution. We also tried to understand the decay profiles in the solid state. That means that for how long the phosphorescence or the delayed emissions last even when the source of light is turned off. We found that for the N-butyl substitution, it was 90.8 microseconds. For the isopropyl substitution, it was 114.2 microseconds, and for the alpha-methyl benzyl group, it was 114 microseconds. Especially if you try to see here, as the bulkiness of the N substitution was increased from N-butyl to alpha-methyl benzyl group, the decay profile also, the decay tau average, or which is the time which takes to decay the particular phosphorescence state, it is also increased. So we observe a much more longer phosphorescence as the bulkiness of the N substitution is increased. Concluding our study, we found that 4-bromothalamides are a promising source, as they show consistent phosphorescence in the solid state, although no phosphorescence was observed in the solution state. But in the solid state, both fluorescence and phosphorescence was observed at 460 nanometer for all the three different substitutions involved. And this particular idea suggests that that the main core involved in the phosphorescence is actually the 4-bromothalamide core. We also found that as the end substitution was much more bulkier, as the bulkiness of the end substitution got increased, that likely led to a much more compact structure in the solid state, and thus a better intensity of phosphorescence was also obtained. And at the same time, it took longer. It actually showed longer phosphorescence lifetimes, as we could see with the alpha methyl benzyl substitution with the highest lifetime of 140 microseconds, and then isopropyl at 114 microseconds. Thus, bulkier end substitutions will enhance the rigidity, they will promote the intersystem crossing, and they stabilize the triplet state much more as compared to the less bulkier substitutions. And also, the intensity of the phosphorescence emission is much more better as compared to the less flexible chain, as compared to the flexible chains. What the future scope involved: to study more the topic into detail, crystallography, that is the XRD and the Hertz field analysis, should be conducted to validate this solid state analysis, that hypotheses that we have given here. To molecular packing and the intermolecular interactions as well. Also, we should expand the substitution scope into more aromatic heteroatom and donor acceptor side chains to study the fine-tuned emission behavior of these compounds and better help cater to the scientific community and to the scientific widespread use of the phosphorescent materials. We should also involve some quantum chemical calculations involved here, like TD-DFT analysis and everything, and also environmental studies should be employed so that we could study at what controlled environments and variable temperatures our phosphorescence occur. So all in all, this particular study proves that a cheap, simple metal-free molecule can show exciting room temperature phosphorescence, and this could lead to a much more cost-effective organic LED materials and organic security aims and a real-time drug tracking system for phosphorescent probes. Thus, this offers a promising standpoint for the future studies, so that much more modifications can be done on this phosphorescent material and they can be fine-tuned. Thank you.